So the next lab we actually tried was finding the, I guess, the correlation between voltage and the angle of inclination. So we did this on 12 p.m. and what we had to do first was just find the angle of inclination itself. And the way we did that was we found the object outside, just found its length and the width of its shadow, and just used trigonometry to find that the theta would be 68 degrees. But that's not the theta that we're focusing on. We need the angle from the normal for our solar panels. So using basic similar triangles, as you can see here, we found that an alpha of 22 degrees would actually be the angle, our normal angle, from which we get the maximum exposure from the sun at this given time. And this is our experimental data. As you can see, it kind of uh, it reaches its peak around 15 degrees, which is what we expect, and then it tapers off. An interesting thing that we found was that at 90 degrees, although it should technically be zero from the normal, like 90 degrees from the normal, it is 4.27 because whatever surface we were doing it on, it actually reflected off that surface and bounced right back up into the solar panel. So we thought that was very interesting. And then the theoretical, as you can see here, the way we found that was it's just v naught cosine theta because of the angles that align, and we got those given values. And see here, at 90, we would expect the voltage to be zero. And here are both data points combined. I mean, they're pretty on point. We have a little intersection here around that 10 degrees from the normal line, and we're pretty happy with this data. So optimizing voltage, back to you, Malak.
All right. So obviously the thing we did isn't very efficient. You have to change the angle with respect to time to get the most out of it. So what we wanted to see, how do you optimize the voltage without moving it constantly. So maximum voltage occurs when the solar panel is perpendicular to the photon sitting it. That's when it's at the normal. That's the normal line. So the first thing we want to know is, which way would you face your solar panel? So after doing some research, we found it's most efficient to point it towards the equator, because that's where the equator gets the most direct sunlight throughout the year. So, and in Old Bridge, you would want to face it to the south because we are in the northern hemisphere. Next thing we want to know is how much would you tilt it? Well, obviously, what you could do is you could put it on a motor and have it tilt throughout the day, but most people can't afford that or can't do that. It doesn't make any sense. So the general rule is to set the angle equal to your geographical latitude. In Old Bridge, that's 40 degrees north. So you would set your solar panel to 40 degrees. This will capture the most sunlight throughout the year. But if you want to be even more efficient, you could account for the tilt of the Earth. What does this mean? If you go to the next slide. So the tilt of the Earth is tilted on its axis about 23 degrees. So during the summer, sunlight hits us directly as we're tilted towards the sun. But during the winter, the Earth is on the opposite side and we're tilted away from the sun, so we get less direct sunlight. So when we get direct sunlight during the summer, the sun appears higher in the sky. So we need our solar panel to be lower to get the most out of it. So if you go back a slide. So during the summer, what you do is you add 10 to 15 degrees because the sun is higher. And then you subtract 10 to 15 degrees in the winter because it's lower.
All right, so we actually tried creating our own circuits in parallel in series. Unfortunately, we couldn't get this specific one. It was just very complicated to do, and we did not have alligator clips. But from these two, what we learned is that the voltage actually doubles once you do have two solar panels as opposed to one, which makes sense. But what we found a little interesting was that the current actually uh, decreased a little bit, right, Malav?
Yeah.
And we weren't very surprised by that. And as you can see here, this just shows that the current has been I mean, the circuit has been working because the light bulb that we have connected to it has lit up. And here on YouTube, we posted how we just set it up. Should we skip that one? It's a minute long.
Uh, just show it.
You sure? It's okay if we go overtime, yeah? Alright, so here
Yeah.
we have circuit. The circuit. Alright, so here we have the circuit in series. You can see here we're trying to replicate this diagram. So I'll actually start from this solar panel here. The current will travel to the black wire, and it will go right to this amp. Bruh, I'm just trying to listen. 7.2. It goes to this solar panel here, and as you can see, if we get rid of this amp meter, it will be perfectly in series. And then it actually goes all the way to this little light bulb, which lights up, which proves qualitatively that this circuit works, and this quantitatively proves just how much current is passing through it.
Here we have a one-panel circuit. We'll start with the solar panel. We trace it to the bulb, gets it lit up, and then from the bulb we go to the multimeter. Currently it's measuring 62.6 amps. The reason it's changing is because we have to hold the lead to it, so the connection is not very stable. And then to finish off the circuit, we go from the multimeter back to the solar panel. The reason the current is smaller than the two-panel circuit is because we have less voltage. One panel produces less voltage than two.
All right, and now back to our presentation, which is right here. Okay, slide. All right, so that was our little video on circuits, and now we're gonna talk about how do we make a charger. Oh shoot, what the hell happened? Okay, yeah. All right, we're good. One second, I can't hear you. Malav, you
How about now?
Yeah, good.
Okay. So the first thing we did, to make a charger, we collected our materials. We needed a solar panel, obviously, a breadboard, a multimeter, a few rechargeable batteries, wires, and a battery holder. So a brief explanation of what a breadboard is. A breadboard connects wires, so you get to make connections to different devices. The little holes in the same column, they're all connected. So if you need all the positive ends would go on one, and all the negative ends would go on another column. Go to the next slide. So here's a brief, it's a very simple setup. This is our charger. We connect the solar panel to the battery holder and put the batteries in the battery holder. And we put it outside. We let the solar panel charge up the batteries. Next slide. So collecting data. We use our solar charger to charge up our batteries for around 4 hours. So first thing we did is we found the voltage at the beginning before we started charging it at all. And the two batteries had a voltage of 1.99 volts. And the current they were producing was around 61.8 milliamps, sorry. As we go on, can you go to the next slide? Oh, wait, actually go back. As we go on in time, and you can see the voltage stabilizes to around 2.74 volts, and the current drops. Go to the next slide. So how do we measure the voltage and how do we measure the current? So first, when we measured the voltage, what we did is we took the wires on our battery holder. We have the batteries in there, and we just touch the leads, red to red, black to black, to our multimeter when it's set to volts, and it will give us a voltage reading. Current, however, it's a bit more complicated. You have to make sure your multimeter is in series with your circuit. So you have to add the multimeter to your circuit. So what we did is we connected the battery holder and one of the solar panel leads to the breadboard, and then we connected the other parts to the multimeter, and we completed the circuit and we read the current going through it. Next slide.